Okay, so welcome to part 2 of this Grasshopper introduction lesson. Um, so this is the script that we created in part 1 that just kind of drives a simple surface geometry based on a few attractor points. And we're going to start from there as we move forward with a couple of additional tutorials that really incorporate the module. So the first thing I want to show you, which is a really pretty simple tool, is, and I have my module here. So if you guys remember, this was a module that we had modeled in the 3D print workshop, just a kind of really simple minimal surface. Um, and I'm actually going to apply that module, or I'm going to kind of populate that module across this surface. And this is really easy to do, so we can actually do this with any kind of single surface Grasshopper. But what I want to do first is put this or reference this geometry inside of Grasshopper. In order to do that, I'll go to the Parameters tab, I'll go to Geometry. This time I'm actually going to get a component called a BREP, which stands for Boundary Representation, but all that really means is polysurface. So like with our minimal surface, which is actually a collection of individual surfaces that have been joined one, in other words, a polysurface, we actually need a different type of data for that than a single surface. So if I get this little BREP component now, right click and go to set one BREP, see it already did that one because I had it selected beforehand. And I'll turn this off. Okay, and so now we can see that we have our component inside a Grasshopper. Good, that's a starting point. Now what we're going to do here is use a technique called box morphing. Now, second, remember where all these tools are. Oh yeah, under transform and under morph. So if we look in here, there's a couple of components. There's a thing called a twisted box, called a surface box, a thing called a box morph. So we're going to need, and blend box, which what we're going to use is something called a surface box. So I will, that guy. And then we're also going to use that guy called the box morph. So what that allows us to do, first of all, I'll read the input so we can kind of interpret how this will work. It's asking for a base surface, a surface domain, and a height of surface box. So basically what that means is this is our original surface that we're going to make a series of boxes on. It's asking for a surface domain. And what that actually means is how are we subdividing that surface into cells, which will kind of become boxes. And you can see that it's asking for a domain. It's also asking for a two-dimensional domain. So as we kind of discussed in the first tutorial, all geometry has what's called a parameter space. Surfaces have like a U and a V parameter space. And in order to subdivide a surface, in Grasshopper, we need to make a series of ranges. In other words, we wanted to take the top quarter of the surface away. We could tell it to remove the surface between range 0 and 0.5 in the U direction and 0 and 0.5 in the V direction, and it would take away 1/4 of the surface. Fortunately, we don't have to specify every domain range. We can use a thing called divide domain. So if I go to my math and go to domain, I will get a component called divide domain 2, all the way at the bottom here. So again, this is a U and a V. And this actually works the same way as back here with our surface divide. We just need to give it a surface and a number of subdivisions in each direction. So I'll make a number slider just by double clicking on the canvas, type in, and then you can see, and just to kind of give you a, it's giving us a list of pretty kind of complex domains and kind of cross-referencing for us those domains well. Again, this makes a lot easier to do. But it's telling us like for each surface between 1.4 and 2.8 by 0 and 1.2 to kind of separate that as an individual surface. And then again, this is just the domain input on our surface box. That right in. And you can see it's making a surface. So, or I'm sorry, it's making a box. And so again, these number sliders define how many boxes there are in each direction. And they kind of define, or I should say, the height of each surface box will define how deep those become. So once again, I'll make a number slider 10.0 this time. That way I have decimal points. And I'll plug that into the height. Move that slider around, you can see the boxes become bigger and smaller. Again, like we had with the last tutorial, we got to just be mindful of where the surface is going to intersect itself or go through itself. I don't want to make them too, but there we go. Okay, so now we have a target box. We have a box on our surface at kind of in a grid, divided into a grid. So what we need to do is kind of move this geometry to each of those boxes, or morph it in a way. So if we go here to our box morph transformation, it's asking for a geometry. Again, that's our minimal surface. Plug the brep into that. I'll plug again, it's asking for a reference box. And so what it needs to know is what's the box, existing box around our existing geometry to use as a reference, and then apply our new geometry to. And so that's easy enough for us. We can just create a bounding box inside a Grasshopper. I'll double click on the canvas, type in bounding box. I think most of you guys know what this is based on using it in Rhino. But it makes a box around an object at the extents that object. Again, I can plug that into my reference box. And then finally, it's asking us for a target box. So it's going to look at this geometry, look at how it's positioned within that box, and then move it to each of those boxes based on how those boxes are. Plug my surface box in, seconds here, and you can see it's applied that geometry and kind of morphed it relative to each one of those surface boxes. And see it's stretching them proportionally, and it's the other thing I should mention is they're all going the same way. So again, if we were to layer on, we were, oops. Oh, there we go. So if I were to, for example, mirror this, not copy it, so geometry, and then keep an eye on my surface there. Based on the orientation, it's actually going to change the way this polysurface populates the box. So again, I could do that. So if I rotate this thing to a different angle, for example, like 45 degrees, now you can see it's populating it in a different way. Okay. So the position of this thing is important. It will change, again, how it looks at the reference box and therefore applies it to the target box. Now, once again, what's cool about all this is that, you know, everything is still parametric. So we can go back and we can control points. It's going to be a lot slower now because this operation requires rotation, but we can change weight of control point, modify how big surface boxes are. And again, I would just turn down maybe the number of subdivisions you have in each direction. That'll make it run a little meantime. But anyway, so we have more or less a kind of simple module that's been applied to a more complex surface, kind of twisted. morphed. Now, just really quick, I'm actually going to make a copy of this setup. Just tapping Alt. It's because I want to demonstrate like another way of thinking about this. So I'll make my own surface, Rhino, about the same size. I'll reference it in Grasshopper. Surface. Okay, and whether or not you guys know this, I don't know, but you can rebuild surfaces like you can rebuild curves. And once again, when I rebuild a surface, I can change the number of control points it has in each direction. Then we do want to have 3 degrees in the U and the V direction. That'll make it a smooth surface. And make it 1. I'll show you. Now when I move, oops, if I were to move, you can see it doesn't create a smooth surface, right? So when we rebuild, we always want to make sure we put 3 in there. It's a nice and smooth surface. And I'll actually just want it to be 3. I'm actually 4 and 5 and 4. There we go. Okay, so now this is still just a flat surface. And I'm going to replace my morph, my box morph. So now it's also populating this guy. I'll turn that off. But once again, just to illustrate how kind of parameter space works. So right now, because our control points for this surface are all evenly distributed, because we just rebuilt it, you can see that it's giving us an even distribution of modules on the surface. But even if I keep the surface flat, and I'll turn the gumball on for this, and start to move the control points, it's also going to start to redistribute how those modules are populating that surface. Start to see they're curving up and down and stuff like that. So again, this is kind of a method we can use for morphing the geometry even within a single plane. That gives you a kind of easy workflow, and you can see once again it's still flat, but it's giving us a kind of more of a morphed output there. These guys in. So you can also you can preview things in Grasshopper. You can also disable them. So I can select all these components, right click, and hit disable or enable. And again, when I disable them, that means my computer is no longer doing the work to compute any of those components. So once again, so we can kind of get a better sense. I'll put it in. And then there we go. Those are morphed module surfaces there. And so you can see this one's actually kind of 3-dimensional. It's like weaving in and out. And this one's still completely flat, but it's also kind of morphing or changing based on that kind of how we move those. So what I also want to do though, because if we look at these 2 surfaces, they're all the same thickness. So we haven't modified the thickness of the module at all in this process. So there's one other method that we can use in the box morph transform, which is rather than make what's called a surface box, where we just make every box the same height, we can make what's called a twisted box, and that will create a box between 2 surfaces. Now, in order to do that, I'm going to go back to transform, morph, and get this twisted box. And you can see that guy's got a whole bunch of different. Now, I'll go back to my surface here. So what I want to do first of all is actually make two different surfaces rather than just one. And so rather than repeating this whole set of inputs here, I'm going to just copy a few components. I'm going to copy my populate surface. I'm going to copy my surface grid, copy my move, copy my amplitude, my vector amplitude, and I'm going to copy my remap and my domain. Those 4 or 5 components. And I'll go copy paste. Okay. Now we have 2 surfaces. And what I can do is move actually, I guess I do kind of need to copy more stuff. Let me just hit Control Z and go back. So rather than do that, I'm actually going to copy everything that's like downstream from my surface divide. Yeah. Control points. Okay. Then I'm going to take all my control points on this guy and put them on one side. And then I'll take all my control points for the other one and put them on the other. That way I'm kind of pulling the surface apart in 2 directions. Now we have 2 surfaces. Oh. So again, that's where you might want to put it in decimal so you get a little steps. Okay, so all I've done is I've copied that set of components that are creating the surfaces, and I've moved my control points. But now you can see I have 2 different surfaces there. What I want to do now is, rather than making a box based on a single surface, I'm going to make a box between 2 surfaces, between these 2 separate surfaces. Now you can see what's going on there with our twisted box is it actually wants, I'll hover over the inputs, it actually wants a corner point it wants all 8 corner points of every single box. Now, in order to do that, what I need to do again is just subdivide my surface. So I'm already doing that. In order to actually make it into separate surfaces, so like I mentioned before, this is just our domains that tell us that tell Grasshopper how to subdivide. We want to actually apply that to subdividing the surface. So I'll go to Surface, Analysis. There's a component called isotrim. Yeah, excuse me, isotrim. This works like the surface box did. It requires a surface input and a domain input. And it just creates a kind of grid of subsurfaces based on how much we divide it and on the original surface geometry. So that's great. We now have the kind of grid on our surface where we want. But we'll copy that actually for both surfaces. And you'll see it. You'll notice I didn't copy the UV because we want each of these 2 surfaces to have the same number of subdivisions. That also. That way we have like one box or one surface on each side to make a box between. Now, if we look at the outputs, we have individual untrimmed, it says, surfaces. That's each one of these little squares is its own surface now. But we still need to get the corner points of each of those surfaces. So we can use a component in surface under analysis called deconstruct brep. And it's that one that looks like a little cylinder with an explode icon around it. And I'll plug my surfaces into that. You can see it's outputting a bunch of different values. It's outputting faces, edges, and vertices, which are corner points, right? X, Y, Z coordinate corner points. And you can also see and so going back to our first tutorial where I talked about grafted lists and flattened lists, It's also putting every single set, so each one of these little squares has 4 corner points, obviously. It's putting each set of points in its own sub list. And this is a great example of where we want to have a sub list. Because that way it knows, okay, the first surface, copy point 0 to first surface in this list and its own point 0. So all we got to do now is actually separate each of these lists into individual outputs for our A, B, C, D, E, F, G, H. Then I'll get a component called a list item. I'll plug my vertices into that. And a list item just returns a single item from a list based on the order of that list. If you remember back to our attractor points where we have 4 points in a list, you can see that not only are they in a single list, they're in a specific order. That 0, 1, 2, 3 represents what's called an index. That's like if we want to get the second item in the list, for example, we have to tell it to look at index 1 within a specific list. So with our list item, and if I'll plug the items into that, and I can specify an item index, specify that index as 1, this will return a single point, right? So we can see there's 0, there's 1, go all the way up to 3. We can pull out a specific item within the list based on what index we tell it to look for. Now, what's nice about a grafted list is that it's returning all the zeros for each branch, for each grafted individual list. So we can do them all at the same time, which is great. And the other thing that's nice about this list item is if we zoom in far enough, we'll see these little plus icons appear at the output side of the component. And you can see it's returning their index. And our index by default is set to 0, so that's the first item in each list. And it's returning the second item and the third item and the fourth item, but all its separate outputs. And that's exactly what we need. So we can plug I into A, plus 1 into B, plus B, plus 3. Copy that as well for my other surface. And now you'll see that I've created a box in between these two surfaces for each subdivision. And I can, whoa, okay. Leave it like that. Okay. And now we can keep the same structure as before. So we have our twisted box, we have our bounding box, and we have our geometry. And so rather than using our surface box output, we're going to use this twisted box output. Put that into T. I'll unpreview everything. There you go. So not only are we getting that same kind of morphing in this direction, you can see that it changes thickness kind of along the length surface there. Now just really slow. All right, I'll tell you what, I'm just going to do that. Oh, yeah, I didn't explain this. That's a good point. So in Grasshopper, when you have something that's kind of done or like you want to save it as an iteration or as real geometry, again, like this component contains the information to make that surface, but it isn't actually physically in Rhino yet. So what we need to do if we want it in Rhino, we want to be able to do stuff with it in Rhino, is we need to do a thing called bake. So if we select the component and right click on it, we can bake it and we can specify a specific layer. that it wants to be baked to. We can also select that component and just hit insert on the keyboard, which is what I did just then and before, earlier when I made these other spaces. And then you can see I can select it, its physical geometry. I know. And then around, or I can scale it, distort it, do whatever I want. And so there we go. That kind of wraps up the techniques that utilize the box morph thing. I think I'm going to stop this video here. And then there will be one other video utilizing part one and just showing how to like kind of modify or drive the geometry of a module based on an attractor point, similar to what we did before. Go ahead and sign off now.